Thank you. I guess we're trying to get back on time here, so they've started me into my talk, which is fine. I guess the first question I would ask is, I'm an analytical chemist. I spent my whole career making methods to measure things. So, why would you really care? Well, to be honest, if you want to buy a piece of real estate, what's the first thing you have to do now? You'd better measure the dirt to make sure there's no buried drums and stuff on your property. You might get stuck with the cleanup. If your family doctor says, oh, I took a blood sample and you've got this deadly disease, well, the first thing I would say is take another sample and measure it again, because people do make mistakes. So I'm not going to talk about that. But the general steps in how we develop methods, it's the same for everything, really. So I hope that if you learn how we go about the process of developing a method and how we measure things in the environment, you'll have some good questions when someone else comes up here and says, hey, I found 5 parts per billion of something in your backyard. You'll know the right questions to ask that person. So I'm going to talk about the steps to analyze water. I'm going to talk about what is trace. You've already heard about some units, parts per billion, parts per trillion. I'm going to talk a bit about that. How do we know we're right? When you see how we go through and actually do the measurements, you can see there's a lot of work that goes in it. There's a lot of steps, and we have very expensive instrumentation that works really well. And I'm talking about, if you're scared by the last presentation, it scared me a little bit. There's a whole bunch of new things that challenge people like me to, in the future, it's going to be even more difficult to do our work. So, the first thing is probably you wouldn't even think of this. You have to decide why you're taking the sample. What are you trying to do here? And I'll go through the different objectives. And the methods we use depend on the objectives. Let's put it this way. If you need a 10-cent solution to a simple problem, you don't go and give it to the $1 million piece of equipment, because it costs a lot of money. So you have to decide what it is you really want to get. We have to take a sample for testing. Prepare the sample for analysis, because we can't take the water and the soil and just stick it directly in our $1 million instrument. And then we do the analysis. Finally, we look at all the quality control we put onto it to make sure we didn't make any mistakes. And then we ask ourselves, have we answered the question? Do we know why? We knew why we took the sample. Did we get our answer? If not, then you've got to go back to the drawing board. This is job number 1 for the Ministry of Environment, and I think for every other government agency who has a laboratory. Ensure the safety of our drinking water. Sometimes, I went to high school in Sarnia, and in the St. Clair River there, they've had lots of cases where some companies along the river would accidentally spill something in the river, and then they would call us out. Some years ago, they had the St. Clair blob. It still pops up in the news. I was the supervisor of the Dioxin Lab when that happened, and that was a fun part of my life. So, emergency response. Sometimes we have to take a company to court. They won't clean up. We try to work with companies first. We don't want to put them out of business, but we can't let them pollute. So sometimes we have to take them to court. Now, if you're going to take them to court, how are you going to convict them? Because of the samples we took. Well, we'd better be right, because if there's any hole anywhere in the work we do, the defense attorney will find that hole and they'll get the samples thrown out. You get the samples thrown out, no case. Sometimes research. For example, if I'm developing a new method, then we may have to go take some samples for practice to see if our new method works. So the methods we use depend on our objectives. And it all comes down to money. Everything costs money, and we try to get as much work done with the resources we have. You all have the same challenge in your life. Representative sampling. Instead of spending an hour explaining what this is, let me show you something. These are old, by the way, because that's how far back I go with the ministry. And I just happen to have some really good newspaper headlines. look at the date, April 23rd, 1988. Toxic chemical crackdown is working. And it says discharges into the Niagara River dwindling. That's a great story. Now, a month later, about 5 weeks after this, there was another headline in the paper. Dioxin pollution 10 times worse. It's risen tenfold. Now, you don't have to be a scientist to realize we're dealing with the Great Lakes. It's a great big body of water. You can't be dwindling the pollution, and a month later, it's increased by 10 times. Well, that's because of sampling. If I go take some samples at the U.S. side of the Niagara River, where all those, Hyde Park and Love Canal and all those places are, I guarantee you the levels are going to be much higher than if I go right across the lake to the Canadian side and take some measurements there. It's the same lake, but your results are going to be much different. You can't just take 1 or 2 samples anywhere in any of these bodies and think you have exactly the right answer. You might have to take 100 samples or 50 or 500. It's not so easy. Sampling containers. If you think you've got some pollution in your backyard and you want to call us about it, please don't take your old peanut butter jar, fill it up with water, and then mail it into us. I guarantee you we're going to find lots of stuff in there, and probably almost none of it's from your backyard. We clean all our containers before we send them out. We spend a lot of money making sure they're clean so that when we do get a positive result, we know it's from the sample, the place we took it, and not the sampling container. Also, it depends on what you want to do. If you're doing metals, like Professor Shodek talked about earlier, he does metals. I'm more an organics guy. So my sampling containers are usually glass. His sampling containers are usually plastic. Shipping and storage. Now, if you're concerned about bacteria in the water, for example, that's not my area, but you can't leave it sitting over a long weekend and then come in Tuesday and then do the E. coli readings. Because when it's sitting in the jar, those things can grow. They can reproduce. You may have a really high reading, but the water might be okay. So when we get something like E. coli, it's sent to us refrigerated. We have to analyze it within 24 hours, or we have to throw the sample out and get a new sample. If it's something like dioxin, we can leave it sitting in the container for a week, 2 weeks, 3 weeks. It's okay. There are some metals that we do. When we take the sample, we actually have to add acid to the sample to make sure that it stays the same, because you can get the metals oxidizing just sitting in the container. Whoop. Yeah. I get this on my home computer all the time. Thank you. So, sample preparation. Here's where the real work starts. We have to extract the samples out. So like I said, usually we can't just stick the material directly into our expensive instruments. You know, it's like having an expensive appliance at home or a really expensive car. The more expensive it is, the more it breaks down. We have to remove interferences. Now, what are interferences? Let me give you an example. On a beautiful day like today, you're outside, the bright sun, you look up, you hear a plane, you want to look at the plane, you look up, and the sun is blinding you, so you can't see the plane. You know it's there, but you can't see it. You don't see it because you can still hear it. The sun is an interference. It prevents you from seeing what you want to look at. How do you take care of that? Well, a really good pair of sunglasses might do it, or if you have a special instrument, you can take a picture and then develop it and see the plane in the picture. So we have the same thing when we do our work. Because the thing we want to look at, dioxins, and for me, it might be lead for Dr. Shodek. That's not all that's in the water. Everything else you can think of is in there too, and some of those things prevent us from doing the work. So we have to take them out of the water before we can look at what the analyte is. Then we have to concentrate it, because when you get to these really low levels of detection, well, our instruments, even though they're really good and really expensive, they're not so good that you can see just a few molecules. So we have to concentrate the sample. So what are we testing for? The extraction, if you're doing organics like PCBs, dioxins in my case, pesticides and herbicides, you might be concerned about those in an area like this. You'd use an organic solvent because these compounds are more soluble in the organic solvent than they are in the water. In fact, they're not really very soluble in the water at all. Sometimes, if we're doing surface water or river water, we have to filter it first, because if there's a lot of particulates there, our extraction methods for particulates are different than the extraction methods for the water. So we filter it, we extract it from the filter separately with using another method, then we extract the water with another method, and then we combine the extracts later. Drinking water, we usually don't filter because there's very few particulates in drinking water. So this is an example of water extraction step, and you can't really see this, but there's hexane in there. There's the water, 1 liter water sample. There's a vortex caused by the spinning. The hexane and the water mix together really well. And then what happens is we take the hexane out from the top. We do this 2 or 3 times. And we've extracted 95 or 99% of the organic chemicals. This is work we did when we first did dioxin testing in drinking water many years ago. We have much better methods now, but we set up all these flasks of 1 liter samples, and we did 4 liters to get our detection limits low enough. We had to extract 4 liters of drinking water so that we could detect dioxins at parts per trillion levels. This is very laborious, as you can imagine, and it uses a lot of solvent. We now have filter discs we can use. We pour the water through the disc and everything stays in the disc. Instead of, several liters of solvent, which is not good for the environment, we can use maybe 50 milliliters of solvent to get it off that disc. So our methods improve as time goes on. I remember this work though. It was a lot of fun. For solids, we do something like what's called a oxide extraction. And I'll explain how it works. And you all should know, you should understand this very well. If you drink coffee, I'll explain that. That's our solvent. It boils at a fairly low temperature. The vapors go up here. There's cold water running through here, so the vapors condense and drip into our solid sample here. When this fills up, the solvent spills over back down into the flask. The chemicals we're looking at, PCBs, dioxins, they don't boil at the same temperature. They take a much higher temperature, so they stay there. Fresh solvent goes through, and the chemicals stay there. We do that overnight. We come in the next morning, and we've got 95% of our organics are down in here now. The reason you should understand this, if you drink coffee, is coffee's extracted pretty much the same way. What you do in coffee, you have your coffee, ground coffee beans, you have water, you boil it, the hot water goes through, they call it percolation. It's the same thing. So if you drink coffee, you understand this extraction. And you know all the other variables too. If you have fine ground coffee, you get more extracted out than if you have coarse ground coffee. So it's the same with us. We want to extract everything out that we can. If we leave these interferences in, we're going to get the wrong answers. Our samples will get thrown out of court. We won't be able to help you and to tell whether that sample was toxic or not. So we have to get our interferences out. The interferences aren't necessarily bad things in terms of health effects. The things we're looking for are the bad things. But if we don't take the interferences out, we won't be able to look for what we're looking for. We use chemical operations called cleanup. And they're not hard to understand. For dioxin, we still use this. When we do our extraction, sometimes the sample still looks very clear. Usually it's maybe a yellow color, but it looks like a clear liquid when we do our extraction. We put it at the top here with some solvent and let it drain through this particulate material that we've coated with different chemicals. The chemicals we've coated with trap the things we don't want. For example, this is a real sample we sent through. It looks clear when we put it in, except a yellow color. All these colors, you can't see them in the original sample, but they're stuck here. What are those things? I don't really know what they are, but they're interferences. They're stuck here. We wash the things we want to test for, wash through. We put them through another column, which is a different chemical principle, and then we have something that's 99.99% pure with the things we want to test for. Then we have a chance to do this work at really low detection levels. It's still not good enough. We can't put that solvent in our instrument yet. It's too dilute. Let me give you an example. When you, around your home, when you get your home chemicals and stuff, or even if you get things like Tylenol and you read the label of what's in it, it'll be 0.1% of something, or 1% of something, or 5% of something else. Well, the levels we're looking at start 1,000 times below that. Parts per billion is 1 part in 10 to the 9. That's where we start. 1,000 times below that is a part per trillion. 1 part in 10 to the 12. We can look at things that dilute in the environment. And the level we're at right now in our lab, parts per quadrillion. We can see things that are 1 part in 10 to the 15, but we have to go through all these other steps I showed you, or else we can't do it. We usually extract maybe a liter of water, 100 milliliters to a liter is our typical sample size. Our final sample size is 10 to 100 microliters. So we have a 10,000 to 100,000 dilution factor. Let me show you what the sample looks like before we inject it into our instrument. That's a microliter. That's 10 microliters right there. In a, even just measuring out 10 microliters, we do it using a syringe, but even that is not easy to do. This is the Commissioner Street incinerator in Toronto. It was closed down because of mainly dioxin pollution. You have to go up the stack and build a sampling apparatus around the stack, and we measure the gases as they go up the top of the stack. That's not fun to do. This is from the roof of our building to do what's in the air. We have a filter, and we basically just suck the air through the filter. And we can extract it using that Soxhlet apparatus I showed you, and we can tell you how many parts per trillion dioxin is in the ambient air. I saved this one till last. How many people know about the ministry's Guide to Eating Sports Fish? No sports fishermen here? Okay, a few of you. The ones who are still awake, put their hands up. This is how we analyze fish, because we do the analysis for that in our lab. That's 10 grams of fish in concentrated hydrochloric acid. So that black gunk is there. We extract it. After we do that, we put solvent in there and shake it with the shaker. We do that 2 or 3 times. Then we go through the process I showed you. Now the fun part. The part that gets all the glamour is the high-priced equipment we use. But if the fancy stuff is the equipment I'm going to show you now, if you go back and take a lousy sample, none of this will matter. There's an old computer saying that applies to analysis: garbage in, garbage out. We'll give you an answer in any sample you want to send us, but if you don't have a good sample, you won't get a good answer. So the whole chain has to be done properly, because our analysis result is only as good as the weakest link in the chain. We have hundreds of different types of instruments to use for the analysis, but I'm only going to talk about 2. For metals, This is the kind of instrument that Professor Schodek uses in Germany, inductively coupled plasma mass spectrometer. Well, it's a big, long name, but let me show you what it is very basically. It uses, you can call it, it's not really flame, it's a hot plasma. Call it a flame, but it's a hot plasma to atomize metals in the sample. How hot? It's about this guy'd be good in the lab. We have backup instruments in the lab too. Anyway, see, it's so hot the mic couldn't handle it. It's about as hot as the surface of the sun. That's pretty hot. We make the metals. It's so hot that the metals become metallic in this plasma. We get them out of their oxidation states. Everything else they're combined with, it's just the metals in the flame, in the plasma. And the mass of the metal, lead, 206, 208, there's a bunch of different isotopes of lead. We measure the masses. So we measure the mass of the metal. We count up the number of measurements that we have for that mass, and we can tell how much stuff's in there. This is what the plasma looks like. So this shot's been taken behind a safety barrier. I can't put my face right in there. It wouldn't be good. But that's an ICP-MS torch. It's the way everybody does metals now. There are other methods of doing it, but this gives us the best detection limits. For organics, which is the area that I've spent most of my career in, we use what's called a gas chromatograph mass spectrometer, or a GCMS. There's like dozens of different kinds of these instruments, and they cost anywhere from $100,000 to $1.5 million for one instrument. And they all have different capabilities. This is one of the cases, you don't always get what you pay for. When you pay more here, you get lower detection limits, you get better features. The basic principles are the same for all of them, though. So we have to take our sample in that little vial I showed you. We get maybe anywhere from 10 to 100 microliters final volume. We inject 1 or 2 microliters into a hot injection port. So I'll show you this full instrument, but we inject it in there. We inject it into what's called the GC column. This is a hollow tube, 0.2 or 0.1 millimeters diameter. It's very small. You can't really see the hole when you're looking at it, but we inject the sample in there and it goes around the column. Now, at the end of the column, the compounds come out one at a time, basically. I'm showing soil because water, a drinking water sample would never be dirty like this. For soil, we inject the sample here. This big thing at the front, that great big thing, is the solvent, because all our samples are in solvents at the end. And then afterwards, things that are really light, like methane, really light molecules will come out first. And then heavier, like PCBs and dioxins, will come out later because they're heavier. The heavier the molecule is, the longer it takes to go through our column. It's pretty much as simple as that. And you can see there are hundreds of things. And given a sample like this, we might be able to tell you what 100 things are. And there's 100 things we can't tell you what they are because they're not in our computer database. So this is the whole system. We inject our sample. It goes around. Light things go through fast. Slow, big, heavy molecules take longer. This is at atmospheric pressure, the pressure we're under right now. This is high vacuum. And in between the two, the molecules go in here. A beam of electrons, you know what that is? That's an incandescent light bulb. There's a beam of electrons, really, or you can get a beam of electrons that way. Just heat a filament up really hot in a vacuum, and you'll get a beam of electrons. They break up our molecules. We get a molecule like methane, the chemical structure CH4. You'll get an H by itself, you'll get CH3, you'll get CH4, you'll get CH2. All the pieces that you can make from that molecule will appear. The mass spectrometer separates all of those pieces out by mass. And then we plot them, mass, and how much of it we have, and we get something that's a pattern we call the mass spectrum. Each molecule has its own fingerprint. This is the one for the most toxic form of dioxin, TCDD. This is what its fingerprint looks like. These are all masses of individual parts of the molecule. We broke up when we injected it into that instrument. We plotted at the end. Anyone in the world sees this pattern, they know they've got TCDD. So it's very, very powerful technology. Now, the better news, this is one of those $800,000 piece of equipment. That's not very cheap. It's called a high-resolution mass spectrometer. If we want to get lower and lower detection limits, we use fancier and fancier tools. This is that gas chromatograph. This is where the molecules come into high vacuum. They get broken up and ionized. This is a great big magnet. It's powerful enough to lift a small car. When you put a charged particle through a magnet, it deflects it, just like light going through a prism. It's very analogous to what's happening here. So that's how we separate the different masses out. This thing's called a double focusing. The magnet focuses, and we've got electric field at here which also focuses. So it focuses it twice, which means we can get really good resolution of our masses and really good detection limits. So when someone wants to measure the PCBs in your backyard or the trihalomethanes in your drinking water, and you want to ask them some intelligent questions, you should know some things that we always ask about our methods. Detection limit's the first one. I come to you, I'm a consultant, and I say, well, I checked your backyard, we didn't find any PCBs. Your first question should be, well, what was your detection limit? And the consultant will probably start to sweat. Well, it was 10 parts per billion. If they tell you the detection was 10 parts per billion, that means there could be some PCBs there at 9 parts per billion. So it's very important to understand what this is. And whenever we develop a new method, one of the first things we do is find out what our detection limit is. If it's not good enough, we have to go back to the drawing board because we have to look at these low, low levels. Accuracy. How close is it to the real concentration? I'm not going to get into that. We need another week. But we have standards, just like on a weigh scale. You know, you have an equal pan balance. You put a weight over here. You put the thing you're measuring over here. If the balances are equal, it means the two weights are the same. So we have standards that we extract and run through our whole procedure, just like I showed you, except we know how much was in that other sample. And then we compare our unknown sample to that. That's what we do. Precision, related to the measurement uncertainty. So you might get an answer, but maybe if you did the sample 3 times, one answer would be here, one would be here, and one would be here. So which one's the right one? Well, that's a good question. Now, when you read, I think we've got a reporter sitting here, so I'm not referring to you, but you read these things in papers all the time, because how do you explain these low, low detection limits to people who haven't had the training that I've had? I mean, it's not that complicated, but I've been at it for 30 years. So, you know, it took me a while to get to know it too, believe me. So I made these up, silly comparisons. 10 parts per million, which is pretty high concentration, is like the speed limit of the 401 versus the speed of light. That's 10 parts per million. 1 parts per billion is like 1 second in 32 years. Parts per trillion? Well, the reason I don't like these comparisons is because you can't get your mind around that. No one thinks this way. So here's how I like to show people about detection limits. Again, I know dioxin best. That's why I use so many dioxin examples. A nanogram, 10 to the minus 9 grams of dioxin, sounds like not much. That's how many molecules? That's like million, billion, 2 trillion molecules in a nanogram of dioxin, because molecules don't weigh very much. That's a lot of molecules. So when we do our sound, when we inject that sample on our instrument, we're injecting, you know, quite a few molecules. And the machines we use are good enough to see it at that level. Now, I have a colleague who works for the Atlanta Centers for Disease Control. In the dioxin area, he's one of the best in the world. And his detection limits are a bit better than ours for what he does. He's getting close to this level right now. 1 attogram, 10 to the minus 18 grams, which is still 2,000 molecules. Now, we could probably not even see, we could never do an environmental analysis for 2,000 attograms. You know why? Or 1 attogram. We couldn't even extract that few molecules out of our sample without losing most of it. But we're getting close to this level now. This is how good we are these days. So when you get down to that level, you know what the problem is? You start finding every molecule everywhere you look. That's the problem we're having now. We'll never do dioxin below that level because we'll never get a blank that's clean enough. Now, accuracy and precision. If you throw some arrows at a target, there's the target. Now, none of the arrows have hit the target, but because of random air, wind, and you have a shade, whatever, if you take the average of those 3 readings, it's right on. So this actually is an accurate method. This method is very accurate. This method is not as accurate, even though the arrows are all together, but it's very precise, which means if I shoot the same way all the time, I'm going to get the arrow in the same spot. Now, so why don't we just, everyone wants the accuracy. So why don't we take all our measurements 3 times and then take the average. This works if the errors are just random errors. Take a bunch of readings, take the average, you're going to get the right answer. And statistics works. The problem is, if you're doing something like dioxin, it costs $1,000 a sample. 1 sample, $1,000. So what are you going to get, right? You're going to send in 1 sample because that's all you've got in the bank, and we're going to take 1. You can't get a reasonable answer for anything by just taking 1 sample. Now, I'm going to tell you something that happened when I was in a dioxin lab. This is a true story. In the early days of doing water, we did lake water on 3 consecutive days. No particular reason. We were doing some research, and we wanted to see if things changed. So on the first day, that's our detection limit, 0.1 to 0.3 parts per trillion, which at that time was pretty low. On day 1, we got 0.2. This is the same general area in the lake. 0.2 parts per trillion. On day 2, we got 0.4. On day 3, we didn't get anything. Now, our detection limits are 0.1 to 0.3. Now, to me, these numbers are all the same. There's no difference between those 3 numbers. Because, you could get that much variance just from routine error. Now, a reporter wrote about this. I wasn't trying to do anything funny or anything, but here's the headline. Whoops. My headline's disappeared. There it is. Levels of dioxin double and then disappear. Now, if you don't know what I told you today and you read this, they double and they disappear. I mean, your first thought was going to be, what the hell are those guys doing up at the lab? How can it double and then disappear? Well, the numbers were all the same because they were all within our limits of error for that method. So that's something to remember when you see these numbers. Put a grain of salt on them, maybe a whole box even, although salt's bad for your health. Now, what do we got to do? Not only all of the chemicals that we're looking at, the PCBs, dioxins, herbicides, pesticides, trihalomethanes, all that stuff. Anything you put in your body And then later on, you go to the bathroom, well, some of it's going to get flushed down there. So pharmaceuticals and personal care products, makeup, anything that you use, cough remedies, it all gets down the sewer eventually and gets into the environment. Perfluorinated compounds. You know, Stain Guard? You used to be able to buy Stain Guard. And Stain Guard works. But these fluorinated compounds, now we don't like them. We think they're toxic. So now we're taking them out of circulation. But they're there in the environment. To disinfect the water, the main method people use is to add chlorine. And when you hear about the Walkerton story, chlorine disinfection was not done right, and that was a big problem there. Well, when you use chlorine, you get these disinfection products which are carcinogenic at high levels. Well, why do we use it then? Well, because a little tiny bit of these chemicals is better than cholera. And that's the choice you have. We have other ways of disinfecting water people are doing research on, and they have different byproducts that end up in the water because of that. So one of the big jobs that we're doing now at the ministry is we're trying to identify as many of these different compounds we can, and then someone else's job is to find out whether that might be toxic or not. Brominated flame retardants. You know, at home, your seat cushions, your TV sets, your computers, especially if they're old, they're probably soaked in these chemicals. Because if they catch on fire, the fire spreads much more slowly when you have these chemicals. Gee, we found out they're toxic, and now they're banned. And now we're taking them out of the market. But there's a lot of products that still exist that they're soaked with these chemicals, and what are we going to do about it? Algal toxins, you might find that around this area more. If global warming is appearing, if the temperatures get as high as our last speaker said they might, you may get more algal blooms. Summers may last longer. These algal blooms may get bigger and more powerful, and you may get more of these toxins that appear in the waterways. Organometallic compounds, tin and lead. Paints used, fungicides use some of these compounds. Paints used for boats used to have a lot of these chemicals in them. So they're around the environment all over the place. So all of these chemicals are there, and the future of my work is going to, do more of these chemicals at lower detection limits, faster and cheaper. That's my job, is to do that. Now, how many chemicals are in the environment? Chemical Abstract Service lists all new chemicals. Like these professors who were speaking today, if their job was making new chemicals, they publish a paper when they make a new one, and they send a message to these guys saying, I made a new compound, here's my proof, list it on your database. So they have a database of all the chemicals we know about. I updated it August the 1st for this talk today. 32 million organic and inorganic substances in their database. 32 million. 15 million of these chemicals are commercially available. So how many chemicals have we been talking today? A few hundred. The periodic table, that's not that many metals. So we've got our work cut out for us for a long, long time to come. Here's our big new tool. This is the, I've saved the big one for the end, the $1.5 million piece of equipment. The Fourier Transform Ion Cyclotron Resonance Mass Spectrometer. Now, the only thing I'll say about this is the capabilities are so far above everything else we have. We've got the only one in the world, by the way, right now. The Ministry of Environment has the only one in the world of this instrument that's configured the way we have it for environmental work. And when I go back at the end of my vacation next week, I'm going to be working on this thing. These other mass spectrometers work on mass, like carbon's mass 12, oxygen's mass 16, and hydrogen's mass 1. So you add these masses together and get your molecular weight. This thing is so sensitive, we have to take into account the mass of the electrons, in addition to the mass of all the other protons and neutrons. So this is really a fantastic tool. We're going to be using it. One of the big applications is to look at your drinking water to see if we can find out new things that might be there. So I hope you just remember some good questions you can ask other people like me who give results to you in the future. I hope you now have a few good questions to ask them from this talk. This is a grad course in chemistry in like 30 minutes, so thank you very much for not falling asleep. That's me next week in the lab.